let's see. So warm up. All I would like you to do is think of different equations that use multiple variables. So different equations you've encountered in a math class, physics, chem, whatever class. Do you think they represent functions? I'll leave that there, open-ended there. So try to think of like maybe 2 or 3 different equations that you can think of that you've encountered that use multiple variables. Try to do more than 2. More than 2. I got everything. I believe so. And then just share out some of the equations with your groups. Any equations that you've created with multiple variables.
Yeah. I mean, the first thing that comes to mind would be they're all variables, but it's only a function if like you take it in the right perspective. Yes.
Oh, that's all you know?
They also think about like the equation of the sphere. Think about it like things that have one or the other are only a function on a certain.
Yes, they do, right? X,
I guess it's all like another thing I think about multiple variables. There you've got like the matrix, yeah, all of those. You take a one variable. Thank you.
All right, guys, let's see. All right, share out with me one equation that you found, Dylan.
F equals MA.
F equals M, usually this M, right?
Yes, I get.
MA, okay. Thank you. Did you and your group decide if you think this is a function or not?
It is a function, but only if you take it as a function as a whole thing, because each of the individual variables are their own function.
So let's just say yes or no. What do you think?
Yes.
All right, we'll go with yes. Yes. Okay. And then we'll discuss it today and see if you want to change your answer or not. Okay. Jacob.
E equals MC squared.
E equals MC squared. What did you guys say? Function or not a function?
It is.
You say it's a function. All right. Keith. Oh, Ethan?
X squared plus y squared equals r.
R or R squared?
Oh, r squared. My
R
bad.
squared, okay. So function or not a function?
I think it's technically not a function, right? Because wait,
Well, you said no,
Wait a
but he's
second.
saying yes.
wait.
I picked Ethan, so I'm gonna go with your answer.
Because, okay, if you make it in terms of y, it's a function,
Because
right? So therefore in that term.
Because like okay, for a single y, right? For a y value, you get multiple different x values.
Well, yeah.
Wait, shit, no, that's not how it works. I'm sorry.
So you wanna change it to a yes?
Well, I guess it really depends on what you're solving for. 'Cause if you're solving for
This
x,
is very true.
right? Then it's not a function. But if you're solving for r, then it is a function.
Okay. So like if you were square root,
It's not
right?
even, no, it's not, because it could be negative r, so it's not a function regardless of which variable you're solving for.
I'm gonna go with no then.
Yeah.
That seems to be where you're leaning. All right. Patrick. Okay. Sam.
Quadratic formula.
Quadratic formula. Okay. This bad boy here. What is it? Negative b plus or minus. Sing me the song, guys. I don't know the song.
X over 2 plus minus square.
Function or not a function? What do you guys think? Do you always get one x value, or can you get multiple x values? So what do you guys think? Function or not a function? I'll say question mark. I didn't hear like an agreement there. Jacob.
Well, this primitive can be non-zero, so that means that it's not only gonna produce one output, right? These from C,
Okay.
C. So I think the answer is not a function.
You're saying no. Okay, so I'll put no, but then I'll put question mark. Like no, but. All right, let's see. One more. This person is not in the class anymore. Thomas is not here. Eleni.
He said the
Which one?
equation for plan.
Equation of, oh, okay, I'll go with, the linear one.
Yeah. And we said it was.
You said it was not?
It was.
It was, okay. Yes, okay, all right, guys, sweet, so I'm gonna leave this here. Let's talk about functions of multiple variables, define what it is to be a function, and then come back and see if you guys still agree with these guys here. Okay. Thank you. So let's take a look. Okay, new chapter, section 14.1, multivariable functions. All right, let's take a look. We've seen different types of functions so far. So different types of functions up to now. You've seen different things. Let's do input and let's do output over here. So in Calc 1, when you guys were dealing with functions, what kind of things were you plugging in? Scalars or vectors? You're plugging in a scalar, right? You're plugging in a scalar, and then what did it output? It outputted another scalar. Like f of x equals x squared, right? Maybe let's put a little example here on that one. So example, f of x equals x squared. Plug in a number, you get out a number. All right, and I think that's all you saw up to Calc 2. Then you came to this class and it just got crazier. A vector function. What kind of thing do you plug in? In a vector? T, right? You're plugging in a t value. What is that? Scalar. It's a scalar. Plug in a scalar. And then what does it output? Vector. It gives you a vector. So for example, like r of t equals cosine t and sine t. And then that gave you a vector, a position vector that was like drawing your curve. And then we haven't kind of formally defined this third one, but it's still happening, where you input a scalar and it's giving you out a point. That's when you've been parameterizing the coordinates, okay? So it would look similar to this, but sometimes at the beginning of the textbook, when we were looking at space curves, it was just labeling it, like this. Where it's pretty similar to the vector function, except that here, the thing that you're outputting is not a vector, it's just a point on the curve. Versus this is outputting the vector that connects to this point on the curve. Okay?
I guess functions can include other things other than scalars.
Exactly, and that's what we're going to
They
then.
can include everything in the function as long as it's defined properly.
Correct. So in this class, we're about to define, what we're gonna do right now is we're gonna be plugging in a point, and it's gonna output a scalar. That's what we're gonna do right now. Okay, so this is what you've seen up to now. So here, you're gonna plug in a point, an XY coordinate. Let me write it like this. And it's gonna give you a scalar, which we're gonna call Z. Okay? And we're gonna do even more, but right now, let's just go with this one. We're gonna add more to the list as the semester goes on. Okay? Yes. So, let's take a look, let's define what type of function we're gonna deal with in this chapter. So we're gonna say a function f in two variables is a rule that assigns to each pair x comma y a unique number z, which we're going to say is the output of that function. And let me give you a visual of kind of what this is really going to do geometrically. So the points that you're plugging in come from R2. Oh, question and question, yes.
So does it necessarily have to be unique? Because there's functions like z equals x cubed y cubed that usually the same. It seems like
Z equals x cubed
times y cubed.
times
Seems
y
like
cubed.
they would revisit the same z value twice.
If z equaled x cubed y cubed,
Right.
you will not produce two z values. Think how, I guess, how would we produce two z
Oh, what do
values?
you mean, when you say unique, do you mean like this, like just one output?
That's exactly right.
Oh, okay.
Yeah, so it assigns to each pair one unique number z. Yeah, so you're only outputting one unique thing. Sam?
Yeah, what's the word right?
In two variables is a rule that assigns to each pair x, y, a unique number z. Okay, so this pair abstractly can be any pair, but geometrically we're going to think of it as a point. Okay. Oh, sorry, hold on, I forgot to write one little thing here. The domain of this pair, the domain of this function, usually you guys used intervals, right, in Calc 1. But that's because that was only describing one number. You were telling it from this number to this number. Those are the only things you're allowed to plug in. But now you have an ordered pair. So what's going to happen is your domain is going to be something that looks like this. Remember, this math symbol means in R2, our two-dimensional space, such that, and then there's going to be, you want this to be defined. there's going to be a rule here, is defined. We'll look at some examples. But it'll look like that's how you're going to have to describe your domain now. In your range, this is going to be a set of scalars that you're going to be able to output. This one will look more familiar than this one. So visually, what the heck does that mean? That means that your domain, for example, can be a region in the XY plane. A region. D can be some region. Think of like a collection of points, okay, within R2 space. And it's only all these points that I'm allowed to plug in so that the rule is defined, okay? So you're going to grab a point from this region. You're going to plug it into your rule, your function, and it's going to output it on some z-axis that contains all the possible z values, all the possible numbers, a number line, okay? And it's going to output that particular number. And we're going to look at a lot of examples, okay? I know it's very abstract. But what's going to end up happening in 3D space is pretty cool. Pretend this region here is now on the XY plane, okay? It's on the XY plane. And so let's see if I can draw it. Let's say it's this one right here. That region is this region here, okay? And now this point is in 3D space though, okay? So what's the z coordinate of this point right here on the XY plane? It would be 0, right? The z coordinate. So x and y would be the same as this x and y, except that because it's on the xy plane, z is 0 there, okay? And what's going to happen visually, the graph of this, is that it's going to correspond to a point in 3D space. You're going to lift this point. Let me erase the black marks here. You're going to lift this point so that it has this particular z value. So that now that point will be x, y, and z will be the output of that function. Okay? When you guys first learned functions in pre-calc or whatever algebra class, you guys usually did x and y, right? And you guys did a table, an x and y table. You plugged in some x values and it gave you some y values, right? So I want to show you a similar version of that, but for a function of two variables. In a table format though, in a table format. I'll lift it back up, guys. I'll lift it back up. So this will look familiar to your problem set 4. Okay, so here's this table with hella data, okay? It says, in regions with severe winter weather, camera here. The wind chill index is often used to describe the apparent severity of the cold. This index W is subjective to the temperature, the actual temperature outside, T, and the speed of the wind, little v, okay? So what does that mean? That means that W, the index, depends on two variables, the temperature T and the speed of the wind, little v, okay? And so W is a function of T and V, and you can write it as this notation that we're using, okay? The way you use an XY table here is if the temperature is, let's see the temperature's units, Celsius. If it's negative 20 Celsius and the speed of the wind is 40 kilometers per hour, what's the wind chill index here? It's going to be, what did I say, negative 20, right? Here, let me edit it. Hold on. So negative 20 and 40 miles an hour wind, the index is going to be negative 34. That means when you plug in f of what? F of negative 20 comma 40, the output is negative 34. So that's how you would read that table. Okay. Let's say I hold the temperature to be negative 20 Celsius, but the speed of the wind varies, but the temperature stays the same. That means that now the T stays negative 20, but now V is what varies. So I just look, am I going to look at a column or am I going to look at a row? I'm going to look at the row where the temperature is negative 20 and observe what happens to the index as the speed of the wind increases. What seems to happen to the index? It's decreasing, right? Versus if the speed of the wind stays the same, but the temperature changes, now I look at this column here to see what happens to the index as the temperature is changing. You guys see that? W is all these possible values here. All these inside this table. Oh, W, it's called the wind chill index. Yeah, wind chill index. So in this case, for this table, right, the range of this function would be all these possible output values that you see here on this table. And the domain would be all possible ordered pairs of T, comma, with V. That would be the domain of this table, or this function, okay? And the rule here is assigned, the table is the rule. It tells you how to get your output. Question? It's cited, so I want to say yes. Yeah. So you have a similar thing in your problem set. Okay, it's a little different. It's about some other kind of data. Question? Yeah. Now, do you guys notice though that for every temperature and wind speed, you get one unique value of W? You don't get two different values of W, right? Otherwise, it would not be a function. You can't output two different W values or wind chill index values. Question?
So, you said that it is made of every combination of the two variables, so you have to do like a combination map to figure out the whole domain.
Or you would write, exactly, or you would write, I'll show you how you can write that. So, if you wanted to find the domain of this, ain't nobody got time to write all those points. So you would do something like this, where you can specify that T equals, you can say T is an element of the set, and then you would write all these here. You would write negative 40, ... 5. I mean, that's the part where you would have to write it out. Comma, V is an element of the set of all those possible V values, 5 to 80, 5, 10, ... 80. Close the big set bracket here. So that's one way you can write it. Okay. There's more ways, but I'll just leave it at that. Okay.
It sounds like doing some programming.
It does, yeah. Yeah.
Taking more than one parameters.
That's right, yes. And let's see. So let's go to the warm up here. Let me get this out of the way now. So if we go what you guys told me on the warm up, it kind of depends. It kind of depends what you're letting be your input variables and then your output variables. Okay? So for the first example you guys gave me, what would be the input? What would be the input variables? What do you think? Give me the M, give me the A, and I will give you the force, right? So here, F is some function of M and A. Is it true that for a specific M and a specific A, it'll output only one force? Yes, so it is a function. Yeah? Here, what do you guys think would be your dependent variables? M, and C.
C is a constant.
C is a constant?
Yeah. The speed of light.
So then just 10. Okay. So then it would be like this. So is it true that for an M, you get a unique value of this? Yes, so it is a function. Okay. Here's where the discussion was happening. Okay. It really depends which one you want to be the input variables. What do you want the input variables to be?
X and Y.
X and Y. If you choose X and Y, then I'm guessing you guys will let R be that, right? Is it true that for X and Y, you will only get one R?
No.
That one's not true, right? Because let's say you let X and Y equal 2. Or let me do this. Let's let it be 3 and 4. What's X 3 squared? 9 plus 25. So you end up with 25 R squared. But then you get plus or minus. And that does not give you a unique number. Because it corresponds to two different values, positive 5 and negative 5. So this gives you 5 or negative 5. So it's not a function. Okay. Here, what would be your input variables?
ABC.
ABC. So in this case, we're going to do this later on, you have a function of 3 values. What would be your output? X. Is it true that for an A, B, and C, you always get just one unique X? No, because of this plus or minus. Right? So not a function, because it won't give you one unique X value. Okay? Here, hella variables. But what I guess if we think of it as a plane, what is it that's fixed and what is it that can vary? X, Y, Z's are, or if there's an equation of the plane, A, B, C are the coefficients of the normal vector, right?
So it's constant.
Those will be given to you. Those are like this C right here. It's a constant. So this A is constant, B is constant, C is constant. But X, Y, Z are the variables in this case. Okay? But what would be your output variable?
No.
That's where it gets tricky. Because D is technically also a constant, right? So would you want to use all 3 of these to be the input variables?
No.
You can just use 2. Yeah, if we do what we actually have over there, and we want to make Z a function of X and Y, what do you have to do to this equation to express it like this?
You move into C.
Exactly. You isolate the Z's. Move everything to the other side, and whatever ends up on the other side, which is like what? I think it's D minus AX minus BY over C. That is this function. Okay? So now, this is the equation of a plane. This is the function of the plane. Okay? Yeah. All right, great examples, guys. Hit a little bit of everything. Okay, let's see. So let's look at another one. But now one that's a little bit more, I guess, a little more traditional looking. Let's say the homework's going to look something like this. It's going to say find the domain and range of F, and then it wants us to sketch the domain region. And I'll show you what that means. And then here's the function. F of x, y equals the square root of 9 minus x squared minus y squared. Okay. Let's see. So let's say we want to find the domain. We're going to have to write it in this format like this, okay? The domain is going to be a set of points.
So do we have to isolate x and y and find the domain?
No, not quite. So
We can mix them together?
let's go back to Calc 1. Let's say I gave you guys this. How did you guys start finding the domain of that?
So just 9 minus this is also equal to 0.
You wanted to see, you don't want this to be negative, right? So what did you have to mathematically do to show your work to find the domain?
Set it equal to 0.
You set it equal to 0 and greater than 0. You created an inequality and then you isolated, you found the x values that will make that true, right? So we're going to do, where it's under a square root, we don't want the square root, the stuff inside the square root to be negative, so we're going to create our own inequality just the way you did in Calc 1. Okay? So to start finding this domain, I want to include all possible points x, y, such that the inside is going to be greater than or equal to 0. That is what I meant by this, some kind of description that will make the function defined. Okay? Let's say we want, let me move these two variables to this side. Okay? So it's the same set, I'm just moving it around. I'm just kind of doing some manipulation. Okay? And on the xy plane, what would this look like when it equals 9? It's a circle of radius 3. What happens when you have it less than, though? It's going to be the circle, the points on the circle and the points inside the circle, the shaded part, right? So from here, what I had to do was I had to first look at the function and then ask myself, what things do I know mathematically need to happen so that it's defined? This has to happen. And then from this description, I had to then manipulate it to kind of make it look like something that's familiar to me. Okay? From here, I would say, okay, the domain region in this case, on the xy plane, right? On the xy plane, we're going to sketch the domain region, which in this case is a circle of radius 3, and it's shaded. That's my domain. I'm only allowed to plug in points that live in this circle and inside of it or on it. If I pick a point outside of it, like 4, or 3, 3, what happens if you plug in 3 here and 3 here? You're going to get a negative, which will not make the function defined, right? So instead of interval notation, now you're going to write it in set notation, and then some of the problems will have you sketch the actual domain. Let me see here. Okay, questions? Okay, that's the domain. The range was always the harder one. Let's see, range. So here, you're going to want to use this fact that we discussed here, this stuff, that the output is supposed to represent the z variable in 3D space, okay? So because this function is this expression here, that means that this expression is equal to which variable? Equal to z, okay? Kind of like how you remember for functions you would let them equal y, here you're going to let them equal z. If we can manipulate this equation here, how can I get rid of the square root?
Square both sides.
Notice that this tells me that when I square both sides, I have this relationship here. Okay? Actually, hold on, before we do that. Hold on. I'm trying to find my range, right? I'm trying to find my range. So I want to look at all the possible output values. What are all the possible things that can get outputted?
0 positive things.
Can you have negative things? No, right? So since this is equal to z, and we know that this square root here is going to be, let me write it like this. Let me write this so you guys can see. You guys can see something. Is it all positive values? Or do you guys think there's a biggest positive value?
I guess there's a limit there.
Let's take a look. I can rewrite this like this. See that? So what does this mean? This inside of this square root is always 9 minusing something that's never going to be negative. So it's always going to be subtracting from the 9, unless it's 0, 0.
So it's from 0 to 9.
So what's the biggest the inside could be?
9.
The biggest the inside could be is the square root of 9, which is equal to 3. And so therefore, since this is equal to z, and this is squished between 0 and 3, that tells me my z value is squished in between 0 and 3. And so then your range in this case is just a number. So you can write in an interval notation that you did in Calc 1 like this. Okay. Is that cool? Any questions? You gonna repeat anything? Yeah, Charlie.
So the maximum value is square root 9
Because the inside of the square root is always going to be 9. Take away something positive or 0. And so if it's 0, if these two things are 0, 0, then I'm not subtracting anything to 9, so it stays 9. But if these are any other number, I'm going to be subtracting from 9. And it won't make it negative because of my domain. We'll guarantee that it can't be negative. Question? Are you just stretching? Okay. So that would answer this question on the homework, okay? But now I'm gonna just add a little bit. And now let's see let's maybe predict what the graph might look like. Because what we did is we analyzed the domain and we analyzed the range. But now what might be the graph of this function if all the points that are plotted from this circle give me some particular z value that we know has to range from 0 to 3?
It's going to be a half sphere.
Let's take a look. I like the prediction. So let's see. Let's see what the graph of, I guess it's, okay. Let's see. So again, let me go back to what we had earlier. So we have that z is equal to this function. Like that. Now algebraically, I can square it, right? But let's remember the range of z here. We know z has to be from 0 to 3. So if I just square this equation on both sides, I have that this is equal to 9 minus x squared minus y squared, but I still have to respect my range. That still has to be true for my range. Let's manipulate this equation and move these two to the left. And then maybe you'll see a similar, an equation that looks familiar to you now. What's this equation describing? Sphere centered at the origin with radius 3. And so it's true that it's going to be a sphere, but because of my range, right? Because of my range, I'm not allowed to draw the entire sphere. The graph of this function, actually, let's say I did draw the whole sphere. Let's say I drew the whole sphere. Okay? Where the radius was 3. You guys remember the vertical line test for functions? At any given pair xy, I have to produce one unique z value. If I do a vertical line test going in the z direction, let's say I pick a random point here, xy, and you draw a vertical line. How many times does it cross the sphere? Let's say I go like this. Ignoring this part. It's going to cross it here, and it's going to cross it here. So then it won't be a function, right? But, so the sphere itself doesn't represent a function. It's the graph of this equation, but it's not the graph of a function. But this function says that z can't be negative. So it gets rid of that problem by only giving me half the sphere. So now if I use the vertical line test, now it does only cross it once, so that it's a function. Okay? And so here's an example of where you're going to have to use your knowledge of chapter 12 with quadric surfaces and all that to help you sketch the graph. Okay? Okay. Obviously, we were able to do it to this function. But in general, this function can look very complicated. I can have like 9 minus the cosine of ln of x to the power of y. Like it can get really gnarly. And then we can't use quadric surfaces or anything like that to help us. So then we run into an issue there, like, uh-oh, what are we gonna do? Well, luckily, your guys' love of traces comes back. Okay, but they're a little easier, kind of, than traces. So for functions with more complicated graphs, we use the traces z equals k on the xy plane, which in this chapter, so which are called the level curves, and instead of writing the z, I write f of xy is equal to k. But in reality, they're just the traces z equals k, okay? So these level curves make up the functions, what's called contour map. Contour map. prepare something. Okay, here, I want to show you guys something real fast. Do. Let me sign in. Looks like you're still writing that. So let me bring these guys up. We're in 14.1, right? 14.1. Here it is. Okay. So let me show you, because contour maps are they're going to be super important for the rest of this chapter. So I want to show you guys a cool little visual here that I was able to make on GeoGebra. Okay, so here's the example of the function that we just looked at, okay? The hemisphere, radius 3. So what we're going to do is notice the plane z equals k. Oops, it's a little, oh, there you go. Let me change the color. Let's make it orange. Remember with traces, you guys were kind of moving a plane and intersecting it with the surface, right? So we're going to do something similar, but this is the plane z equals k. Notice as I move the plane up and down, it's intersecting it at those red circles, okay? But here's what's important. Those red circles all have the same z value. They all have the same z value. What does that mean? That means that if I focus only on the xy plane, let me move it like this. The points, the xy points right below those red circles are the ones that you plug into the function that give you that z value. Okay? Is that okay? Let me say it again. So on the xy plane, if I look right above on the xy plane, the points right directly below the circle are the ones that you're plugging into f of xy. That output, they all output this z value here. Z equals 1.56 in this example. So they cast a shadow on the xy plane. And these are the traces that you guys have been doing it, but here they're called level curves on the xy plane. Okay? So for example, see how here k is equal to 2? So z is equal to 2. That means all these points on the xy plane on this black circle, if I plug them into the function, what will they have to output? 2. Beautiful. I love it. Okay, good. Correct. They're going to have to output 2, which give you the z value 2, like that. Okay? So as what the textbook's going to do is they're not going to show you this picture. They're just going to show you the level curves now, like this. So all the level curves, like I had you guys do in the chapter 12, are just circles, right? Are just circles that are going to be moving up and down. Or sorry, that are shrinking, but they are going to go as high as a circle of radius 9. Radius 3, because of the domain. Okay. So let me show you some more visuals. This is still going. Hold on, let me pause this thing. Let me share my screen. The textbook now. Get rid of these. So let me go down. So I want to show you guys this picture here. Okay. So here's a different surface of some other function. The graph, remember, the graph of these functions are surfaces. Okay. Down below are the level curves of this surface. Let me zoom in. All the points that are on this big circle of the level surface k equals 20, when you plug them into the function, they're all going to output 20. What about all the points from the smaller circle? What are they going to output? They're going to output 45. So what I need you guys, what you're going to want to do in this chapter is you're going to want to do the same thing you did with traces. You're going to layer your level curves according to the height of z. Okay? What would happen if k was negative 45? What would be the output values if you plug them into the function? Negative 45, which would mean what on the graph? It's below the xy plane. So now z is down below. Okay? You guys, if you ever go hiking or backpacking, you look at a map, and those lines are called the contour map. And what that means, do you guys see right here on this hike path that goes like right here where it says 4,500? That means that if you walk along that path, you will always stay at what height? 4,500 feet. That means that you're always going to be at that same height if you walk along that curve. What happens now if I'm hiking here, but I start walking towards the right? You're going to go downhill, right? So that's later on derivatives are going to come in for that, okay? What happens if you walk towards the left? You're going to be going uphill, correct? Because these are just the mountains trails that are being layered higher and higher and higher till you get to the peak somewhere, okay? Let me show you some more examples with a negative z. Hold on, this is the one that we just did. Hold on, I want with negatives. Hold on, give me a second. They don't have any with negatives. Okay, here's one that's funky. Okay, here's the surface of this weird function right here. Negative x, y, e to the negative x squared y squared. Okay, not gonna expect you to know how to graph that. Okay, don't worry. But you'll be given the level curves, and you do wanna have an idea of what the level curves will look like. So notice, this is the x-axis, this is the y-axis. As you intersect that surface on some plane z equals a number, notice that, for example, if I intersect it right here, it's going to intersect it at these two little circles here. One will be where x is negative and y is positive, and one will be where x is positive and y is negative. So that will be here and here. That's these circles. These little peaks are these little peaks up here. The other ones that you see on quadrant 1 and quadrant 3 are the peaks that come from intersecting it below, down here. If I slice it with z equals like -5 or something, it'll slice it at these two circles made by these peaks. Okay? Let's see. Okay. Let's see. All right. I was gonna do this later, but I think this is a good time because I've been talking way too much. Okay, I'm gonna give you a worksheet. The copier didn't come out that good, so I'll problem number 2, I'm gonna put it on the projector. But I'm gonna give you 3 surfaces. What I want you to do for each surface is determine if it represents a function z of xy. And then if it does represent a function, I want you to try to sketch the level curves on the xy plane. Okay? Let's see, 1, 2, 3, 4, 5, 6. Oh, for number 2, I give you the level curves. There's 2 problems. I give you the level curves of the surface, and I want you to try to figure out what that surface will look like on 3D space. Okay? I'll draw it. It's preparing you for chapter 15.
Are we going all the way to the end of the book?
I think the book has like a chapter 17. We don't do chapter 17. That's different. You want short? Let me pass one back. I'm not sure. All right, guys, try these out. I'm gonna project number 2 on the board because it doesn't look that good. Grab one, pass it back. Grab one, pass it back. All right, let's see. Problem number 2.
So for the level curve, you just need to do XY plane.
On the XY plane. The level curves will live on the XY plane. Correct. All right, that's what it should look like, number 2. Okay? Oh, it still looks like. Make it bigger. There we go. Say it again? Possibly. Yeah. Test these out. So first you want to determine if it's a function or not, if it describes a function.
Not like you miss Y on that axis.
This homework I'm passing out? Oh, not this one. These are old ones. David and here. Ethan. Yeah, there is definitely like. That's very So you're saying that
Yeah, so I think it's taking a lot of take too far.
I'm gonna walk around, there's a homework with no name on it. Oh, yes. Here, I'll put the traces back up, guys.
Here, it'll be like that. Because, it's quite rough. It's a little rough in the bottom, yeah. So these little ridges,
right? Like if
Yeah.
Z is very small, it will cut it as a circle, but it's also gonna slice these tiny little circles here.
So small mountains.
Small little mountains, like little circles like this around it.
But it won't look like that. So I don't know if
All right, guys, hopefully you have something sketched out like this. Part C is a little weird. Part C is a little weird, but it does. That's the main peak in the center here. And the smaller Z gets, the more you're intersecting these little ridges here, which are little circular humps there. So you're gonna get these little humps around it here. Okay. I like you guys' pictures that walking around. They look cooler. All right. For part A, there's gonna be, the homework's gonna test you on, does it look like a paraboloid or should it be a cone? Okay? That's where we're gonna have to be careful, okay? But what's happening here is the farther you're out, the more spread out the circles are gonna be, right, from each other. That means that from here to here, it takes longer to increase z by 1 unit. Versus, if you're really close to the origin, a small little change increases z by 1 unit already. So the fact that these circles in the middle are closer together tells you there's a faster increase of z happening in the beginning. And then the rate, we'll do this later on, as z is increasing, starts to kind of slow down. Okay? When it's a cone, z is going to be increasing. You guys kind of see how it looks like a line? It's going to be increasing at a similar rate as the circles, as you get those level curves. So in this case, your circles will be evenly spaced because the rate at which z is going to increase should be the same. And you'll see that on the homework. Okay? Someone also asked me, if you did not have the numbers here, if these numbers were hidden, would it also be okay to draw the paraboloid going down? And it's possible if you're not given the numbers. Okay? Also, it could also even be like a paraboloid that's lifted up because you're not given the numbers. Okay? So all those will be possible answers if these numbers were met. Okay? Technically, we don't know if that's 0. We're assuming it's 0, right? So maybe that paraboloid is lifted somewhere. We weren't given enough information. Exactly, we didn't count it, yeah. For the second one, because we're intersecting it at these square-looking shapes, oh, I was about to draw on this thing. Your traces here are going to have to, if you raise them at these particular z values, notice that at the origin z is 3, so it's some value here. But as you go out, you reach this circle where z is 0. And so that's where you're going to intersect the xy plane. But then because it's negative, that surface goes under the xy plane. Okay? So it's hard to draw it, but it's like a pyramid that goes under the ground. It's like still going down 3 feet deeper under the ground. Okay? So the homework will have you guys do some stuff with it. Let's take a break, and then we'll talk about how to find them if I don't have the surface, but I just have the expression of the function. So let's take a break. You guys are doing some hard work. Come back at 2:16. 2:16. Let me pause the video. Give me 1 second. I can't. All right, guys. So the mistake was this surface here. Okay, I was wrong. The words I said were right, but the drawings was wrong. So in the center, z is increasing faster, and as you go outward, increases less faster at a slower rate. Okay, so that means in the center, you should be increasing a lot faster, and then it starts slowing down as you go out. So as you go outwards, notice that to increase 1 unit, that means that these circles are farther apart. When you intersect z, right? But as you go from the origin out, notice that these circles are very close, so they're increasing by 1 unit really fast. And so that means that if I raise z 1 unit here, these circles are still pretty small relative to this distance. Yeah. So the circles are not equidistant. Oh, they're not equidistant, yeah. Yeah, they're not. Sorry about that, but thank you for the correction. All right. So now, I want to look at how would you do this if you were not given the surface and you were just given the function. Oh, actually, let me use this one still. Yeah, just use this. So, let me stop sharing. Okay. Okay, so let's use this example again. And let's say we're asked to find or sketch the level curves of, let's say it's that same function then. Like that. Okay. Because these level curves are just z equaling k, right? That means that we're going to let the function equal k. So if I want to start this here, I'm going to start by letting my function equal k. That's supposed to be the z value here. And remember that these level curves are sketched on the xy plane. Okay, don't forget, they're on the xy plane. So you're going to want to see if you can manipulate this equation to look like something that you're familiar with, that you know how to graph on the xy plane. Okay? As we did before, we can square both sides. Okay, you can square both sides, and you end up with k squared is equal to 9 minus x squared minus y squared. What can we do to this so that it looks like something that might be familiar to us? Yeah.
So first, move the 9 on the other side. So you want
Exactly. Okay. You want to flip the signs? Multiply both sides by a negative? Okay. So if I multiply this by a negative, this is going to be negative k plus 9, right? So I can write it like this. Cool? Yeah? Question?
I said, should we try to solve for x or y?
Because both of the variables are being squared, you're not going to be able to write it as a function. Because when you square root, you're going to end up with plus or minus. But notice that the equations of a circle that you guys learned use x squared plus y squared. Right? And so here, if you tried solving for one of the variables, you just end up with a plus or minus square root, which might get a little messy. But here, notice that if this is just r squared, that's the equation of a circle centered at the origin. Okay? So let's plug in some values for k and see what we get. So if k is 0, what does this equation become? 9 plus x squared y squared. What is that right there? Circle of radius 3, right? Give me another k value here. Say 1. What is that going to give you? A circle with what radius? Root 8, or 2 root 2. Right? And let's skip a few and let's put 8 now. Oh wait, not 8. 5. 5? No, not 5. Not 5. Remember, we want to plug it in, right? Because what was the range of your function here? The range was 0 to 3. So k has to be between 0 and 3. Okay. So let's just do 2 and let's just do 3. If you do 2 here, what are we going to get? 5. And then if we do 3, we get we get this weird circle of radius 0, which is really just the what? It's just the point, the origin point, right? So it's kind of like what we did for traces. You're gonna let z equals k, and then it might end up being a hyperbola, it might end up being an ellipse, a parabola. So it's very similar to what you guys did in traces, okay? So then I can sketch out my level curves here. 1, 2, 3, 1, 2, 3. So my circle of radius, which one gave me a circle of radius 3? K equals 0. Ew, sorry. K equals 0. That's a circle, okay? What is the radius of this guy? 2 root 2, but what is that as a decimal? What's the square root of 8? 2.8-ish? 2.8-ish. That means I have a circle that's very close to radius 3, right? So notice that that circle is going to be very close to our bigger circle. And that's when k is equal to 1. What is the square root of 5? It's a little bit more than square root of 4, right? What is it? 2 point what? Right here? Let's say. What did you say, Lucas, in here? 2.23. Okay, so yeah, it's about here. So it would be about also pretty close to this guy here. And then look at that. Right when z increases by 1 unit, boom, you just get the origin. So what is that? What do you think that tells you about the surface? It starts off does z increase really fast or pretty slow? Pretty slow. Let's see. Hold on. Let's draw this.
Wait,
Yeah.
increase or decrease?
Sorry. Let's draw. Here's 3. Okay, you guys see this big circle? What happens to all the output values of those points here? What is z going to be? 0. It's going to output 0. Okay, it's going to output 0. So notice if I plug in, for example, the point here, which is 3, 0, 3 and 0, what does the inside become? It becomes 9 minus 9, which is 0. So then you have a circle of radius 3 that's on the xy plane. Like that, because it's z equaling 0. Then you get another circle that's very close to this one, and the z value only increased by 1. So now it's a smaller circle very close to it, but z, let's say z is 1, 2, 3. Now it's going to be, this is hella hard to draw, sorry. That's levitated 1 unit. And then you get this other smaller circle that has this radius about 2.2. But what are the output values of all those points? 2. They all output 2. So it's again a circle that's very close to it. And now it's levitated 2 units. And then, floop, right there. Because at this point, what is the output value of z? 3. So it's going to be up here. So what do you guys think that might look like? It's an upside down paraboloid, but not necessarily a paraboloid. It was this guy. Half the sphere, a hemisphere. So it was something that looked like that. Yeah? And so in the homework, like I said, these might be ellipses and whatever, hyperbolas, parabolas that maybe like go up or something. Okay. Notice you can't let k be negative, because then this will be undefined, right? Which is because of the range. So it's kind of like all seems different, but it's all kind of talking to itself. Okay. Okay, So, questions on that, on this one here? Well, I erase it. See if you guys have any questions. Let's see. What we got? Okay. So I just wanted to end this section here by now talking about functions of 3 variables. We kind of did one on the warm-up with the quadratic formula, but let's give it a little bit more life here. Let's give it a little bit more of a formal definition. So for a function f, where I'm going to show you guys new notation, where your domain comes from 3-dimensional points, and they're going to be mapped or outputted to a number that lives on the real number line. That's how you read that, okay? So it's a function that plugs in things that come from this set and outputs things that go into this set, like that. And here, we're going to use a triple point here, and we run out of letters, so they usually use W as the 4th coordinate. Okay? We can also, anyway, I'll just say it. Visually, what the heck is going on now? Here's where math starts to get funky. X, Y, Z. So this 3D space is R3, right? Sam?
This is for
What did I write here?
What is full?
Oh, thank you. For a function, I wrote it, the O and F threw me off. For a function f where you're inputting 3-dimensional points and spitting out numbers through this format, now your domain is going to be a 3-dimensional solid. Let's say it's something like this. Like a bean. Some kind of solid. Yes?
I guess this means that these are like level curves because we can't see 4 spatial dimensions, right?
That's kind of where we're going to end up with level surfaces. But we'll get there. Yeah. Okay, so you have a solid. Imagine it's like a blob, literally floating on top of us right now, but it's a solid. Okay? And you're going to get a point. You're going to get a point in 3D space, X, Y, Z, and it's going to be plugged into F on and it's going to give you a number that lives on the number line, and that number, we're calling it f of X, Y, Z. Okay? It's definitely a lot harder to visualize because we can't visualize the 4th dimension, right? So one analogy that you guys can use that's pretty helpful is think of the 4th coordinate being temperature. And X, Y, Z is a point in space, and at that point, that's the temperature at that space, at that point. So if here maybe it's colder, but now a point over here, maybe it's warmer. So that's how you can kind of try to grasp the 4th coordinate. So you plug in a point, and let's say it gives you the temperature. Okay? Which is some number. It's kind of hard to see the graph. Let's just pretend it's temperature here in this case. So, like we did with this example, let's see what a domain might look like for a function like this. So let's say in this case, let's consider the function f of X, Y, Z, and let me have it look very similar to what we did 9 minus x squared minus y squared minus z squared, in this case. So let's just play around with it. Let's see what its domain might be. The domain is going to be a set of three coordinate points. So x, y, z. But what must happen for this function to be defined? Similar to what we did before. We hear from someone from this side. You don't want them to be bigger than 9, correct? So what do we want the inside to not be? Can you take the square root of 0? You don't want it to be less than 0. So we're going to do what we did earlier, and we're going to say, I want this to be greater than or equal to 0. And so as we did earlier, we're going to rewrite this inequality and move the coordinates on one side. That way it looks a little bit more familiar to what you guys did in chapter 12. If this equals 9, what was that in 3D space? It was a sphere of radius 3. It was a sphere of radius 3. That's the domain, not the graph. Okay, this is the domain. The graph, the domain of it. The radius 3. But what does the inequality part say? Say it again. It's a filled-in sphere. It's a solid. It's a solid. It's not just the surface of the sphere. It's a solid, and that's why I tested you guys on all that stuff because it's coming up right here. Okay. So it's a solid sphere. Solid sphere of radius 3. And that means in this function, I'm only allowed to plug in points within that ball. Yes.
Why is it solid?
It's solid because the inequality says that I have to pick points. Think of it like if I plug in a point of a sphere smaller than radius 3, right? Like if I plug in points, that live on a sphere of radius 2, then I know that this sum will be less than 9. And so think of, it's the sphere, the biggest the sphere can be is 3, or a smaller sphere, any smaller sphere, as long as the radius is less than 9. Okay. But this is not the graph of f. This is the domain of f. That's where it gets trippy, because for 2 variables, the graphs were 3-dimensional surfaces. But for 3 variable functions, the domain is a 3-dimensional solid. Okay? Yeah, I already wrote it here. Actually, let me leave this picture here. So, we don't know what the graph will look like in R4. We can't graph it. Okay? But let's use my analogy of temperature. Okay? Here, we graphed the level surfaces so that each point on this surface gave you the same output K. So if we try to copy this to a function of 3 variables, we end up getting something called a level surface. F of x, y, k, x, y, z is equal to k. Okay? And so if I try to do that to this function, I set the function equal to k. So it's going to look very similar to what we did right now. Very similar. Square both sides. This is not the range. This is not the range yet. Right now, I just want to focus on the level surface and the domain, because that's what the homework's going to focus on. And as before, let's get x, y, and z to be by themselves. So actually, this time, let me go like this. Let's move the variables to this side, and let's subtract the k squared. And let's do what we did here. And these were level surfaces. Here, let's see what happens. If k is equal to 0, then I'm going to end up with 9 equals x squared plus y squared plus z squared. What is this the equation of? What is it? It's outer sphere, so the sphere of radius 3. Which is this figure that we drew here, right? Radius 3. But just the surface, not the solid. Okay? Let's put that. Surface of a sphere of radius 3. If k is equal to 1, notice we kind of get the same thing as we did over there. So it's a sphere of radius root 8. K equals 2. It's going to be a sphere of radius root 5. And if k is equal to 3, it's a sphere of radius 0, which is just the origin. I can't draw that the way I drew this here. I mean, I could, but it's going to take me too long. Sure I can, right? So, let me show you what that ends up looking like. Let me go like that so that I don't block this part. So it looks something like that. It looks like different stacked spheres. But let me repeat what we did earlier. On this level surface, if I pick a point on one of these level curves, you get the same output value, right? Okay. Here on a level surface, let's look at the blue one. Every point I pick on that surface of the sphere of radius 3 is going to output 0. Every sphere, it's showing me ones that I don't have here. Okay, but that's what this is doing. It's like you have all these spheres, but all the points on those surface of those spheres give you the same output values. Again, think of them as temperature. All the points on the blue sphere have the same temperature. All the points on the yellow sphere have the same temperature, and so on. Okay? That's kind of what's happening. What we can't do is graph, like here we were able to elevate the level curves with the new z-axis, right? Here, we can't do that because we would have to elevate the surfaces into the w-axis, which we can't visualize. Okay? And so that's where this chapter ends. Okay? It generalizes it to functions of multiple variables, but I'll just leave it at 3 there. Whew, doozy. All right. So on the homework, with level surfaces, it'll be similar stuff that we did here, except that your level surfaces might be paraboloids or ellipsoids, right? So that's where chapter 12 really comes into play. All right, guys, and we're done with section 14.1. So the homework will just have you play with some of the objects we just discussed. So let's see, we got, all right, about 30 minutes. We're gonna discuss limits, and we're gonna continue it when we come back next week because it's kind of a lot with limits. Okay? Yeah. All right. All right, section 14. Am I still sharing my screen? Yes, I am. 14.2, we're going to do limits, part 1. Okay, let me remind you guys what you did in Calc 1 real quick before we jump into this. There's a lot of notation that you guys first learned when you did limits in Calc 1. So recall that if y was a function of one variable, you wrote the following. You said, as x approached a, f of x approached, if it had a limit at L, you said as x approached a, f of x approached L. And then this became the limit as x approached a of the function equaled L. So you wrote that. Visually, what you did is you had a picture here. You had a graph. So this was the graph of y equals f of x. You had some a value here. And then you had, remember that it was possible for a to not be in the domain? Okay, but to make it easy here visually, let's just say it is. And what did you guys train your eye to do to determine the limit? What did your eye do when you were looking at this? You approached it from both directions, right? You approached the x values from the left, and then you were observing the y values and what they were approaching as you went from the left and as you approached a from the right. And then you said, this has a limit, L, if the y values are approaching it as x is approaching it from the left and from the right. It was a lot that you guys learned in Calc 1. Right? You keep the limit. And so this limit was true if the one-sided limits as x to approach a from the left equaled L, and what else?
Yes, x equals, which is a from the right.
From the right, yeah. So right now, when you guys were doing this with your fingers, mathematically, you were doing this in your head, right? If these two-sided limits equal the same number, then you said that the limit exists. Okay? But now, we have z as a function of two variables, x, y. So it gets a little more complicated. Okay? The a that you were approaching was a value that lived in the x-axis, because that's where you were plugging in points from, right? But where are we plugging in points from now? The xy plane. So for me to understand what a limit's going to be, I'm going to get a point xy and try to have it approach a fixed point a comma b. We'll draw this in a little bit, and we're going to say that the function approaches some value of z, L. And so we're going to write it this way. We're going to say the limit as a arbitrary point xy in my domain approaches some fixed point AB, which may not be on my domain, of my function, it'll equal L. That's the notation that we're going to use. And so if I try to get a picture to see when the limit will exist, well, now I have a point that lives on the xy plane. Let's say my domain is some region here. Maybe my domain has holes. Okay? Meaning I can't plug in points from here. It's like a weird amoeba looking thing, like a blob. But let's say my point AB is right here. It's a lot of drawing, but it'll help you out. What does that mean in terms of, like, if I try to look at the actual graph of this? That means that this domain that lives on my xy plane, somewhere here, with some holes in it, let's say there's some holes in it, and this is my point AB right here. Right there, okay? So that is that. But just like we drew the graph of the function here, let's say the graph is some surface that's floating above it. Let's say it's some surface. This is a graph of f. Graph of z equals f of xy. All right, here's where the limit stuff is going to explode on us. How did you confirm that the limit existed again? What did your guys do? It came from two directions. Because on the x-axis, there's only two directions. Coming from the left, coming from the right. But here, I want an arbitrary point xy that could be living here to approach this point. But it doesn't have to do it in a straight path. It could go like this. Or I can have the point approach it like this, some point down here. Or it can go like this, or like that, or like this, or like that. Okay? So there's not two directions anymore. Yes, Jacob?
I guess given there are limited growth, we approach that point. Would we just plug it in,
We're getting there. We're getting there. Yeah, but yeah, that's the issue now. Is like, I can't just do this and that anymore. Like, there's an infinite number of paths.
So do we still have to figure out the direction?
Yes. Yes and no. Yes and no. Yes and no. Yeah, Jacob.
I'm guessing that you can express one of those.
Correct. You guys know a lot of graphs in XY plane. You know how to graph sine waves. You know how to graph. All the graphs you learned in calculus are possible paths. Meaning, I can approach this point using a parabola path. I can do it using a sine, some kind of sine path, and all that stuff. We'll get there. Hold on.
So if there was
But yes, everything you guys are saying is why this is like getting kind of like it's different. Okay? Yeah.
so suppose there's a parabola there, so the parabola is based on x and y, like y equals x squared or something.
Correct. You're going to be able to express y as some function of x, and that's going to help us. Okay? But yes, for this limit to exist, all these possible paths that approach this point, better if this point corresponds to a point here on the surface that has a z value L, then all these paths would correspond to paths on the surface, right? If I elevate these paths, like these points, as these points move here, the output values, just like the way you guys did this. As x was approaching A, you were looking at these y values and seeing it approach L, right? So it's going to be a similar story. Like that. But yeah, so we don't just have two-sided limits anymore. So let's start with the easier question. When did you know this limit did not exist? When they did not agree, when the two-sided limits did not agree. If this limit even didn't exist, then the whole thing can't exist. But if this approached 5 and this approached 7, then the limit does not exist because they don't agree, right? So, what do you think we could do to show a limit doesn't exist in this version?
Sometimes the point is in the bubbles.
If I have a path that gives me a limit, but I have another path that gives me a different limit, then I don't have agreeing limits. All paths have to give you the same limit L. If there are two paths which do not agree, then the limit will not exist. Just the way if these two don't agree, they're not giving you the same y value. Okay?
Is that, the surface that's floating on top of the blue, is that the surface version of the one below it? Is it
It's remember for this example we did earlier? When we started this, the domain was a circle of radius 3, but the graph was the hemisphere above that circle of radius 3. So this is the green, and the hemisphere is the blue.
Okay, so that's the graph over.
This is the graph over the domain of the function. Just the way this was the hemisphere over the domain of the circle. Yeah, good question.
So I guess there are infinite paths there. So if one of the paths doesn't have the same limit as this, so the limit just.
Immediately, the limit will not exist. It should be true for all possible paths.
But I think it's impossible because you have infinite there. I don't know how to say it.
Say it again. It's impossible because what?
It's impossible because you have infinite directions there. So it's hard to say you can include all of them.
Well, that's the beauty of showing a limit does not exist. I don't have to show it for all of them. I just have to show that if I can find two paths that disagree, then the limit won't exist. I don't have to focus on all possible paths to show a limit does not exist. So that's what we're going to start with. We're going to do an example of a limit not existing. It might take up the rest of the class. And then next week, we're going to talk about, well, now how do I show a limit does exist? Because that seems to be the harder thing to do. So question, when doesn't a limit exist? And so, as I said, it's when there are two different paths. So when there are two different paths towards that point, AB, that produce different limits. So let's do an example so you guys can see that, because it's all been very theoretical so far. So here's a similar homework problem. It says show the limit does not exist. And here's the limit. The limit as xy approaches the origin, 0, 0. And the function is x squared minus y squared over x squared plus y squared. Let me draw a picture here for you guys. And then here's that point that we're approaching. is the limit point part of the domain of this function? Can you plug it in? Why not?
Such the denominator would be zero.
You get 0 on the bottom. So notice the point is not in the domain. If it was in the domain, then what do you think we can do? Let's plug it in, like you did in Calc 1, direct substitution. In that case, the limit would exist. It would just be the output. Okay. But here it's telling us to show the limit does not exist. And here's the strategy, guys. There are many ways to approach this point. There's a parabola with the vertex 0, 0. There's a line, y equals x, that crosses this point. Okay? But notice there's also the line y is equal to 0. The line y is equal to 0. You guys see how that passes through that point? Okay? And what's the equation of the vertical line that lies on the y-axis? And x equals 0. But I don't want to mess up that green marker. And then there's the line x equals 0. Okay? And they approach it, I can think of it approaching it from both sides. Let me show you what I mean by that. So let's consider the point xy approaching 0, 0 on the x-axis, where y is equal to 0. This is a little abstract here, okay? What does that mean? That means I'm approaching, x is approaching 0 and y is approaching 0 on points that are only lying on the x-axis, nowhere else. Nowhere else. These points are only lying on the x-axis. Therefore, how do I label it here? This is my function right here, right? Is that cool? That's my function. So on this path, what's true about y? It's always going to be 0. So on my function, now y will always be 0. Okay? So that means that on this path, this function, y is always 0, so I'm going to let all the y's equal 0. And so what do we end up getting here? We end up getting x squared over x squared, right? Which is really just 1. So what are the output values always going to be? They're always going to be 1. So then what is z going to approach? Yeah, let's slow down. So on top of this x-axis, right? If I do the graph on top of that x-axis, what's the z value always going to be? 1. So that means that as the points approach the origin on the x-axis, z will be approaching 1. Okay. So on this path, for points approaching the origin on the x-axis, the limit of z is approaching 1. So now let's do the green one. Let's do the y-axis. And then I'm going to stop for a bit. So consider xy approaching 0, 0 on the y-axis, where here x is equal to 0. So I'm going to do the same thing, but now it's x that's going to be 0. And so therefore, when I plug in 0 into my function for x, it's going to be 0 squared minus y squared and 0 squared plus y squared. So what are the output values always going to be? It's going to be negative y squared over y squared, which reduces to negative 1. So therefore, points that are being plugged into the function from the y-axis now go below the xy plane and output 1, negative 1, sorry. And so their limit is going to be, sorry, negative 1. And since these two limits, there's two different paths that produce different limits, we know that this can't happen. The limit will not exist. Not every possible path will give you the same limit. So then this tells you the limit does not exist. That work with it. It's hard to see why though, like to feel convinced. I know I wasn't when I first took this class. I was like, what? But let me show you. Let's look at it visually, because back then I didn't have this. Let's see if that's true. So let's do f of xy. Oh, for GeoGebra, you do put xy. And we'll read it like that. Equals x squared minus y squared and x squared plus y squared. Okay. So here's the x-axis, the red one. Can I zoom in? Let me see if it lets me zoom in. Are you guys able to see how it like curves here in a funky way? So notice, I don't know if you can see it, but as you go along the x-axis, the graph stays at z equals 1. But as you go along the y-axis, the graph is now at negative 1. And so as you're approaching the origin, those limits are not agreeing. Okay? Does the graph have a point at the origin? No. No, it doesn't. So it's kind of like the analogous version in Calc 1 would be like if the graph is doing something like this. Like that. That's kind of what's happening. There's like a funky discontinuity here. And so there's a discontinuity here. There's a rip, which we're going to talk next week. There's a rip on the graph at the origin. It's ripped. Okay? It's kind of like that. But there's like there's not a hole. There's an actual rip happening there. Okay? Because the different paths, you're going to get different z approaching different values between 1 and between negative 1. So the graphs are kind of like going like this at different values between positive 1 and negative 1. But at here, where the origin lives, there's a rip. No. Yeah, let me see. Let's see if I... stop it. I'm trying to move the whole thing. Here we go. Let me see if I can zoom in some more. See how right here there's like a fold? It's like a pinch. It's like exactly like a pinch, yeah. And it's all pinching towards the z-axis. But on the z-axis, there's a rip there, because on the z-axis, that's where it's 0, 0. X is 0, 0. And it's undefined there, so there can't be points there. There's not a hole, there's a rip. That's new. It's a new thing, because these don't have rips. Okay? But it's like, oh, perfect. It's like at the edge of this room, the edge is not there. There's a rip on the wall. There's a crack. Or a crack. There's a crack. There's a gap here. Okay. Yeah. So yeah, it's like if I grab, you guys ever do those knives inspection? You have these knives, I forgot what they're called.
Oh,
Yeah, sure.
Exacto knife.
Exacto knife. And then on that edge, I just write, all that part of the wall is gone at 0, 0. Right above 0, 0. All that's gone.
Would it kind of be like an asymptote that's just on the z-axis?
Not so much an asymptote, kind of like an asymptote. Yes, kind of like an asymptote, but we're going to look at graphs next week that are asymptotic, where the surface approaches asymptote surface. Hold on, Charlie and the Sam. Yeah.
Did we just get lucky that because this resistance at the limit doesn't exist, or is that did it exist with a limit does exist within the limit?
Yes. Yeah. So like, let's say I did that. Right? Now you can plug 0 in. 0, 0 in. It's in the domain. And so you plug it in, you're going to get 0 on the top and 1 on the bottom. So the limit is 0.
Also, the limit doesn't exist.
If the point is in the domain, yes, but it would have to be a piecewise surface, which we're not going to do.
So you can't just say, oh, the limit doesn't exist. I mean, that's not the limit.
Here's an example of what I meant by piecewise. Which we're not going to do, okay? But if I made this function here, like that, and this is not in the origin, and this is on the origin. So then what's happening is this graph with the crease, the crack, but on the z-axis at the point 0, 0, 3 is a point. It is in the domain, but it won't have a limit. Yeah. Oh, wait, hold on, Sam. It's definitely a discontinuity, which we're going to do next week. How do you decide which path to take? That's going to be where the hard work comes in. Okay? What time is it? Okay. This I can do in 4 minutes. I promise. So let me show you a workaround. Sometimes you can avoid this whole path discussion. There's a nice cheat. Let me show you this cheat. And it uses polar coordinates. Okay? Great, baby. This. So using polar coordinates method, which I don't think your textbook shows you, okay? For polar coordinates, you got x equals r cosine theta, and y equals r sine theta. Okay? If you let r go to 0, regardless of theta, if you let r go to 0, what happens to x and y? Goes to 0, 0. Right? And that's kind of what this limit's doing. Okay? So, since r approaching 0 implies that x and y both approach 0, 0, we're going to end up getting that if I take the limit of a function of 2 variables and I let x be r cosine theta, basically I turn them into polar, this limit will be, if it exists, will be the same limit as what we're looking for. They should agree. Actually, no. If this doesn't exist, this also will not exist. Because they have to agree. Because they're both approaching the same thing. This approaching 0 will force this to approach 0, 0. Okay? So let's do this problem. Let me erase this so you don't get confused. Let's do this problem, but do it through this polar coordinate method. Yes?
Does this work for every point or only 0, 0?
Only 0, 0. Only 0, 0. That's the key here. Which is very special, right? It's like a very special case. So let's do the one from the example. So notice if I let, I'm trying to look for this limit. Yeah, this limit here. That's the one I'm being asked to find. That's this guy here. This is going to be equal to the limit as r approaches 0, but now all the x's and y's, I have to write them in polar. So it's going to be r squared cosine squared theta minus r squared sine squared theta, and then r squared cosine squared theta plus r squared sine squared theta. What can we do to the top?
We can factor the r squared,
You can factor the r squared.
then do translate into cosine to theta.
What happens when you factor the r squared down here?
So it's just
That's just a big fat 1, right? Because you end up with cosine squared plus sine squared, which is 1. So what can you do algebraically here?
we can cancel r squared.
The r's cancel. This limit is still in terms of r. It's still in terms of r. So does this change at all? If your limit is in terms of r.
Totally depend on the theta.
Correct, but the limit is not. The limit doesn't say anything about the theta.
Yeah.
So what ends up happening is this is the limit. This is the limit,
Cosine to theta.
which is a trig identity. What trig identity is that? It's cosine to theta.
But we don't know the theta is valid.
That's the key here. That this limit can be completely different depending on the theta that I use. So it's kind of saying you're going to get a different limit for different thetas, so you won't get the same number.
So it's also DNE.
So it's also DNA because you're getting different limits that depend on theta. Okay? So let's write that here. So this limit will differ for different thetas. And it's not agreeing on one limit. So this tells us that the limit is not the same for all. So it's DNE. It can't exist.
So it all has to cancel out to a number in order for it to be not DNE.
For example, let's say this was x cubed. If this was x cubed, then this would be r cubed. And then when I cancel this, I'm left with an r. Now what happens with this limit?
Oh, I see. Okay.
It'll become 0.
Yeah.
Boom. Regardless of the theta, they always have to be 0. And that's what we're going to do next week. All right, guys, we're done. Good job.